Hi friends, so today we are going to start one more optimization tutorial, and today we will talk about complex step gradient. So this is a relatively new method which has come out as far as numerical differentiation is concerned, and we are going to look at that today. I am Dr. Ganguly. So today we are going to discuss the complex step derivative. This method is based on using complex numbers. First, we are going to show this method for a single variable function. Then we are going to demonstrate it for a multivariable function where we are going to calculate the gradient vector. Finally, we are going to solve a simple optimization problem using the BFGS method and the complex step derivative gradient. Remember, the BFGS method has the form xk plus 1 is xk plus alpha k dk, where the search direction dk is obtained by solving the linear system bk dk is minus ck. Here, of course, c is the gradient vector, d is the search direction, and b is the matrix which is built up in this quasi-Newton method. And of course, x is the design variable at point k, x here is the design variable at point k plus 1, and alpha k is the one-dimensional step size. So if you want to revise these particular theories, then take a look at optimization lecture 23 on the BFGS and DFP method, and also on lecture 24 I discussed numerical differentiation using the classical techniques like forward difference method, backward difference method, and central difference method. So today we are also going to develop Python code to showcase this particular concept of the complex step derivative. Now, I did not make any lecture video on this when I actually first came up with the optimization lectures. So this is kind of an extra you are getting out of this tutorial. So let us just recap by looking at the forward finite difference formula. And this formula has the form that the derivative df by dx is approximately equal to fx plus h minus f of x divided by h. Now here, of course, you know that this is something you can obtain from Taylor series, and you can also get this from the fundamental definition of the derivative in calculus. And here h should be a small number for this particular formula to work out well. But the problem is that when you are doing this on computer, then if h becomes too small, then the value of f at x plus h and the value of f at x are going to become very similar. So you are going to require subtraction of two very small numbers which are almost similar. So I should say two numbers which are nearly similar rather than very small. And therefore, this particular problem of subtracting two similar numbers is something which creates problem in the selection of step size as far as the classical numerical differentiation methods are concerned. And the complex step method we will discuss today is going to solve this problem. Now we can get the formula for the complex step derivative by looking at the Taylor series expansion of the function f at x plus ih. And if we take this expansion, it comes out like this. So you have some terms which are real terms and some terms which have the coefficient I in them. Remember, I is root of -1. You also know that I square will be -1. So some of the locations where there is a I square term, you actually get this negative sign. Now, once we have obtained this expansion here, what we can do is that we can take the imaginary part on both sides of this equation, and that's what I have done here. And then you can see that on the right hand side you will get only h f dash x term. This term will come here, and then you will get the next term is minus h cube f triple dash x by factorial 3 and so on. Now if we look carefully at this equation, if we were to reduce h substantially, then certainly this will give us a good estimation of the derivative f dash of x. Now to do that, let us just simply write f dash x using this formula here, and we do that here. We divide this complete equation by h and then bring f dash x to one side. So then we get f dash x is this term here plus the terms involving h square and so on. Now, of course, you know that as I drive h to be smaller and smaller, these terms are all going to become 0. So I'm going to be left with this as the key term here. That is f dash x could be estimated by this expression here. Now one of the interesting thing in this formula would be that if I reduce h substantially, these terms are all going to be zeroed out, and there is also no round off because I'm not subtracting two small numbers here. So that is a big advantage of this method. Let us now write these two formulas here. The first formula is of course the complex step derivative method, which tells you to take the imaginary part of the function at x plus ih and divide that by h. And then we have the typical equation for the forward finite difference derivative, which you all know from the previous lectures and tutorials, that is fx plus h minus f of x divided by h. Now here, like I mentioned before, you are subtracting two numbers which are very nearly similar, and in the complex step derivative you do not have to do that. So now if we want to extend the concept to partial derivatives, we would essentially have this equation here. So if I am taking the derivative of f with respect to the design variable xi, then what I need to do is I need to perturb xi in the function by ih, and then I need to take the im part of that particular function divided by h. And then what I can do is that I can use a very small h here. So for example, a value like 10 to the power minus 20 is a good value to use. We are going to justify that very soon. Let us now start writing some Python code to check out how this method works, because as far as this method is concerned, the theory is very simple and the programming is actually the very important part here. So let's do this question 1, which tells us to write a Python program for the complex step formula. And we have to use the following function. Fx is x to the power 5. And I'm going to check this for 4 different values of h, that is 10 to the power minus 1, 10 to the power minus 4, 10 to the power minus 10, and 10 to the power minus 20. Now you know that in most finite difference type derivatives we use some value like 10 to the power minus 4. That's considered a good value. But if you use values like 10 to the power minus 20 for h, then the function value at x plus h and at x is going to be very similar. So you are going to get round off there. Let us write the Python program here. So of course first I bring in numpy, and then I define a very simple function here which does most of the work. So this function is complex step and it has f, x, and h. And what I do is I create z here or z as a complex number. So essentially this complex number has two parts, x and h. So remember, this is going to give me x plus ih here. And then I'm going to return the imaginary part of this complex number fz, that is simply this fx plus ih, and I'm going to divide that by h. So very simple piece of code here where I'm using the fact that Python has this built-in thing called complex, and that's going to help me a lot. Now I need a simple function to actually give back the function. So the function f of x is simply return x to the power 5. That's the function here. Now let's calculate this derivative at x is 1. So I put x0 is 1 and I put h is 0.0001, that is h is 10 to the power minus 4. And then I simply invoke the complex step function and give it f, x0 and h, and then I print out this dfx, which is the derivative being returned by the complex step function. So that should print out dfx here, and you can see I get this 4.99 all the way, and this is essentially identical to the value which I can get by differentiating. So if I differentiating f of x is x to the power 5, I will get f dash x is 5x4, and I get f dash at 1 is 5. So essentially this is good enough for most problems out there. Now let's just try to reduce this h to 10 to the power minus 10, which I have done here. The remaining things in this program are exactly same, and then you can see that dfx is actually printed out as 5 by the program here. Now I'm using Google Colab to actually do this programming. You can use Google Colab or you can use the Jupyter notebook out there. Let's try this for 10 to the power minus 20. Now this seems an extremely low value, but here of course you are seeing there is no subtraction taking place in the numerator term. So what happens is that I get the derivative as 5, and here you can see I have put in h is e to the power minus 20. Now just as a check, let us check out h is 0.1. So again, if h is 0.1, I get 4.9, which is a rough approximation. So you can see that taking a value like h is 0.1 or something which is pretty large is going to give me a weak approximation of the derivative. But as far as this method is concerned, its strength lies in the fact that I can take very low values of h and I can calculate very accurate derivatives. So again, it's very interesting piece of code which you can see here. You can write this in various languages out there. But the interesting thing is that Python has this nice way to represent the complex number. So remember, the complex number has two parts, x and h, and so I can very simply form x plus ih by simply declaring it to be z. That's the nomenclature we typically use for a complex number. And then I simply use this function to return directly the complex step derivative to me. Now let's add some complexity to this problem. We are now going to write Python code to calculate the gradient vector, because of course single variable functions are very simple, but in optimization we typically have multivariate functions. So for example, let's go back to our old function, that is x1 square plus 2x2 square plus e to the power minus x1 minus x2, and we are going to calculate the derivative of the point 5 minus 5, and we are going to use h is 10 to the power minus 20. Let's first start with by writing Python functions for f of x and grad f of x. So again, as far as the first function is concerned, it simply returns to you this mathematical function here. And as far as the second function grad fx is concerned, it's returning to us the gradient vector here. So remember that I have to use np.exp because exponential requires me to invoke numpy for calculation in these particular problems. So now let us take a look at the function which calculates the gradient. So essentially we are going to call this function the CST function, and CST stands for complex step derivative here. It's going to take in x and h, and it's going to return to me the gradient vector. So what I do here is that I try to write this math in terms of Python. So what I'm doing is I'm creating here z1, and this is going to take a complex number which is x0 plus h. That's essentially I'm perturbing x0 by h, and I'm going to create a second vector z2, and this is going to take in x1 and h. So here I'm perturbing the second design variable x1 by h. And why I perturb one of the design variables, I keep the second design variable the same. So you can see in the first term z1, x0 is being perturbed by h, and in the second term z2, x1 is being perturbed by h, and here x1 is being kept at the baseline value, and here x0 is being kept at the baseline value. Now once I have calculated this z1 and z2, I can essentially calculate the function value at z1 and z2. I can take the imaginary part of this function and then I can divide it by h. So this should give me the gradient vector for this particular problem. So let us try to write a program for this. So I'm again taking the same point 5 minus 5. I have the h value as 10 to the power minus 20, and then I start with this x0. I have h here. I print complex step derivative, and then I print out the gradient vector and the complex step derivative. And so you see these come out as identical. So this is extremely interesting. Now of course I chose a very small value here, and so as far as complex step derivative is concerned, it gives very good results because I am choosing a very low value of h. So as far as truncation error is concerned, remember that was proportional to h square, that becomes extremely small and almost negligible in this problem. So now we are ready to use this complex step method in the optimization process. So let us use the BFGS method and we are going to integrate it with the complex step derivative. Let's look at this function, that is a function which is a quadratic e by 2 x1 square plus 3.5 x2 square plus pi x1 x2, and I have created this function such that the Hessian matrix comes out very nicely. We are going to start from the point x0 is 5 minus 5 and we are going to use the value of h as 10 to the power minus 20. Now, before we proceed with the optimization, let us just look at the math. So if we have the function here, we can calculate the gradient vector and set it to 0. And we immediately obtain the stationary point as x1, x2 is 0. So this is the stationary point. Now, the H matrix can immediately be obtained by taking the second derivative. So remember, this is the gradient vector. So if I take the second derivatives, I will get e, pi, and 7. So this is a nice matrix and hopefully the BFGS method is going to be able to recreate this H matrix using the B matrix. Let us just check this matrix out whether it's positive definite or not. So we clearly see here that the H matrix is positive definite because the eigenvalues are both greater than 0. So the point we have is a minimum point. Now let's write the Python code for the function and the gradient vector. So again, I have simply put in the function here. Remember that NumPy has some built-in things such as np.e and p.py, which I can use for this known constants. And then I also return the gradient vector as a vector here. So this is essentially coded version of the math given here in red. Let's also print the H matrix because we are going to use this H matrix to track how the BFGS method works out. So again, the matrix is coded in here as E, pi, and 7. And I'm going to use this simple function in the one-dimensional search. So this function returns to me the function value at xk plus 1, that is at x plus alpha d. So this is a function which we are going to use in the equal interval search next. So of course, you know that we require a one-dimensional search in optimization. So I'm using this method. So we essentially proceed as follows. Alpha is delta, 2 delta, 3 delta till we reach q minus 1 delta, q plus 1 delta. Once we have bracketed the minimum between these 3 points, we can essentially calculate the minimum point as alpha star is the midpoint between alpha L and alpha U. And then I'm going to divide delta by 10 and I'm going to continue on these for loops until I have converged on the value of alpha star. Now in this program, A essentially stands for alpha. Take a look at optimization tutorial 7 for more about the one-dimensional search method which we are using here. Let's again recapitulate on the CST function, the critical function here. So again, what I'm going to do is encode this mathematics given by the red equation in this Python code, and I'm going to use the fact that Python has some built-in things such as complex, and complex is going to take a pair of numbers, for example x0h, and return to me the corresponding complex number here. Now BFGS formula is well known. For example, B0 starts as I and then BK plus 1 is built up using this expression here. Now remember that YK and SK are both vectors which we built up in this method. YK is the difference between the gradient vectors at point K and K plus 1 and SK is alpha K dk. So if I calculate SK and YK, then I can actually calculate these two matrices here and then I can update the BK matrix. Of course, I start with B0 is I and then I will build it up here. Now remember, B0 should always be positive definite and symmetric, and so I ensures that. This is the BFGS function. So I have slightly modified it here. Of course, we have discussed this function in detail before. So we start with B0 is I. You see here, I start with X is X0, the starting point. Then I have the for loop. Now in the for loop, the first thing I do is I call this CSD function and I put in the gradient C in from what is coming out of the CSD function. I also print out the two derivatives here. One of these is of course obtained from the calculation from the differentiated part of the gradient vector, and the second is the complex step derivative, which I call C numerical here. I built up all these vectors, for example S, for example Y, and then I use the BFGS formula given here to update the B matrix, and finally I solve the linear system given by BD is minus K minus C using this particular solver here. And the one-dimensional search is done here, and then I go on and I print out the B matrix and the H matrix. Now this process, this for loop is going to continue until I have converged. So convergence I determine by the fact that fxk and fx at the previous value is less than tolerance. So I'm using that to converge here. Let us write the main program. Essentially, I have x0 as the starting point. I have tolerance, tolerance 1D, and max as three numbers which I use inside the code. I have h is 1e minus 20, and then I print BFGS method complex step gradient, and then I call the BFGS method here. Now in the complex step derivative, I am using a very small h, so that is e to the power minus 20. Now let's write the most interesting part, which is the final result of this program. So you can see here very nice results, and you can see the convergence is of course very rapid. As expected, the convergence is to 0 0, which you can see here. More interestingly, you can see the H matrix is completely same as the B matrix. So as far as this problem is concerned, B is equal to H. H is of course E pi pi 7. These numbers you can see out here, and interestingly the B is also exactly the same. Now one of the things you can see here is that the gradient which is coming from the mathematical calculation exactly matches the gradient which is coming from the complex step derivative. So this is something which is extremely interesting here. The complex step derivative numbers are extremely accurate. Now you can take this particular problem and extend it to 3 dimensions. So I will say that take this as a function, have this as the starting design 5 minus 5 5, and use the complex step derivative along with BFGS to minimize this function, and at the end of this process check if the Hessian and B matrix are same. Now remember, they are not all the time going to be exactly same. That's only something which you generally see in quadratic functions, but they are going to be pretty close, so that's something you can check out and see. Now when I was doing this method, I came across various values of h which are being recommended by different people. So I did some research in the area, and I found this particular statement in a paper that generally h below 10 to the power minus 8 is recommended, and you can use very low values of h. So in fact you will find some people using values such as this here, extremely low values, and this is given as a kind of extremely low value below which I guess you should not go. So I would say for most part h is minus 10 to the power minus 20 is going to work out very well. If you are more interested, take a look at this paper here for some modern discussions on this particular derivative. And this paper I think is downloadable on the web, so you can check it out and see. So finally, to summarize, I'm going to state that complex step derivative method is a very interesting and good method as far as numerical derivatives are concerned. You can see from the formula here that you can use very low h, and this is something which is going to help as far as the correctness and accuracy of the numerical derivative is concerned. You also see that compared to the finite difference derivative, you have solved that particular problem, that you are not subtracting two similar numbers as h becomes very small. And the mathematics of this, though it deals with complex numbers, is actually inside the functions you create for the numerical derivative. As far as your problem is concerned, it essentially deals with real numbers all the time. So as far as the complex math is concerned, that is something which is not really being used in the main programs and so on. So this is a very interesting part of this method out here. So I hope you enjoyed this method and you can put it in practice in some of your practical work out here. So I think we have finished with numerical differentiation now, and we are now going to start proceeding to the next chapter as far as this tutorial is concerned. So I will see you in a video sometime soon. See you then.